So let's talk about the fundamental types of crystalline solids, and these divisions are based on what the individual particles are. So we can look at crystalline solids that have molecules as their base unit, ions as the base unit, or atoms as the base unit. And talking about atomic solids, we can divide those into three groups based on what is holding the atoms together. Are they non-bonding, just held together by dispersion forces? Are they metallic, held by metallic bonds? Or are they bonded by covalent bonds throughout the entire structure? So a molecular solid, you've got molecules as the individual particles. The molecules are held together by intermolecular forces. And the strength of that's going to depend on the type of molecules you're talking about. But these tend to have low to moderately low melting points because the intermolecular forces are fairly weak. You can have the same molecules crystallize into different structures. They're called polymorphs, many shapes. And the specific polymorph that you're looking at can affect other properties. An example here that you might want to read about in the book is chocolate. So when cocoa butter crystallizes, it can crystallize in 6 different forms. And depending on what form it has crystallized in, the melting point will be different and the texture will be different. Good chocolate is this polymorph 5 that is firm, it's got a good snap, it's smooth and shiny. It melts in your mouth, and that's the best kind. When chocolate gets this white kind of coating on it, that's called blooming. And as chocolate sits, the crystal structure can change. And so you can have a really good chocolate bar and you let it sit at room temperature for a long time and you open it up and it looks like that. Well, it's not that it's bad to eat. It's not gone bad. That's not mold or anything. But the molecules have rearranged themselves and the consistency and the texture of it is not going to be the same. It's not going to make you sick, though. You can still eat the chocolate. Making chocolate is very much of an art. Ionic solids, we've got individual ions, and those ions are held together by ionic bonds, the interactions between cations and anions. Because ionic bonds are very strong, these tend to have high melting points, and we're going to talk more about these later. Atomic solids. The first type is non-bonding. So we just have individual atoms, such as xenon. Xenon atoms, you can make xenon into a solid, but you have to get it really, really cold. These will form closest packed structures to maximize their coordination number. They're going to have very low melting points because all that holds them together are dispersion forces. And actually the only examples that I can give you are noble gases in their solids forms. So this obviously is not a super important type of atomic solid. Metallic atomic solids are very common. Anything metallic is going to be a metallic atomic solid. So here we have individual metal atoms, and they're held together by metallic bonds, that electron C model. And that's a pretty strong bond in general, so metals typically have high melting points, but then there are things like gallium and mercury that melt at much lower temperatures. So there's variation. Then there are network covalent atomic solids, and these are really interesting. Here we have individual atoms that are bonded to each other by covalent bonds. Those covalent bonds go throughout the entire structure. It's not that we have individual molecules stuck together. In a sense, the one piece is one ginormous molecule. Examples are diamond, graphite, silicon dioxide, or quartz. Here, the crystal structure is limited by the constraints of the covalent bonds. So we learned a lot about those, right? You can get sp3 hybridization, you get a tetrahedral structure, or you'd have a linear, whatever the hybridization is of the orbitals, that's going to limit the bond angles that are possible. And so here we do not see crystal structures form based on high efficiency. They're limited by the geometry of the bonds. So this is the sort of question we should be able to answer. What type of atomic solid is Au? Well, what kind of an element is Au? It's a metal, right? Even if we don't recognize that Au is gold, we can find it on the periodic table and it's in there with the metals. If it's a metallic element, it's a metallic atomic solid, right? So this is metallic. Another sort of question, which solid would you expect to have the highest melting point? Well, again, we need to look at the things that were given here and see, well, what kind of things are they? So here we've got magnesium oxide. What kind of a compound is that? It's ionic, right? Magnesium and oxygen. So this is an ionic compound. Ionic compounds are ionic solids. What holds it together? Ionic bonds. I'm not trying to be tricky here. It's an ionic compound, makes an ionic solid held together by ionic bonds, right? We have magnesium ions and oxide ions, and they're attracted by the opposite charges. And those charges go throughout the whole structure. So in a sense, these aren't molecules, but it's the same all the way throughout. It's not individual molecules stuck together. It's ions repeating all throughout. So ionic bonds, very strong. Here we have I2 solid. Well, what's I2? Is it an atom, an ion, or a molecule? It's a molecule, right? So this is a molecular element. It's got molecules. So that means it's a molecular solid. What holds molecules together as a solid? Intermolecular forces, right? So here we've got ionic bonds. Here we have intermolecular forces. And then the last one, krypton, atom, ion, or element? I'm sorry, atom, molecule, or ion. It's an atom. So this is, those are atoms. This is an atomic solid. What do you think? Does krypton have a high melting point? What state is it in at room temperature? It's a gas. It's got a really low melting point. Because what's holding this together? Intermolecular forces, but just dispersion forces. Now, it's not asking us to rank these, it's just asking which is the highest melting point, which is held together by the strongest forces. Magnesium oxide, right? So this is the sort of question that probably will show up in the final exam. And it doesn't require a lot of detailed knowledge. You just have to be willing to sit back and think about it for a minute. Okay? These are concepts that I'm pretty sure everybody is pretty okay with, right? Identifying an ion versus a molecule. Yeah, so I2, that's a nonpolar molecule, right? So that would be just dispersion forces. And the krypton would also be dispersion forces. And so then comparing the two of them might be a little tricky, and the only thing we could do would be look at mass. Krypton has a mass of about 84, and iodine's about 127, but there's two of them. So I would predict iodine to have a higher melting point than xenon.
Could you also compare them where it's natural state krypton is a gas, whereas iodine is
Yeah.
a gas?
Yeah, we can also, because those are elements, iodine and krypton, we can look at the periodic table and we see that molecular elemental iodine is a solid at room temperature. And xenon is a gas. And so sometimes those sorts of things, it's like, well, actually the answer is like on the periodic table, you just have to look in the right place.